Hey guys, how you doing? Hullabaloo, Connect. All right, so this is Coach Scott, Purple Wave Chemistries, Quantum Mechanics. What are we talking about here? Sounds scary. So, we had some problems with the Bohr model, if you remember, right? It answers some questions, but it still has some problems. All right, if you had more than one electron, a multi electron atom, it didn't fit the math that it did for hydrogen. It also could not explain double and triple bond bands that would appear in the spectra. All right, so also couldn't explain why some energy levels are closer together than others. So what happened? It takes quantum mechanics to provide a more accurate picture of what we're seeing. So what is quantum mechanics? It's a revolutionary theory that explains the behavior of very, very small particles like atoms and subatomic particles. It's the most proven, most accurate, tested theory of physics. It's been being tested for like the last 100 years. It explains the energy states in complex atoms and molecules, and it explains the brightness of spectral lines. So, uh, it describes what's going on with these very, very, very small particles. Now, it's based on the evidence that very small particles, like electrons, don't behave like anything we experience in the macro world, what we can see. Sometimes they act like particles. Sometimes they act like waves, like light waves or sound waves. This is called, underline this, wave particle duality. So there's nothing that we have experience with that explains how an electron acts. Only through experimental data have we been able to accept this theory. It just works. Now, if we understand how very small objects like electrons behave, all right, and how they do it, yeah, you won't get that until your junior or senior level of college if you major in physics. There's courses, there's degrees on quantum theory. Um, the experimental data, it is what it is. But how do we understand it? That's pretty challenging. So we're just going to assume, for our purposes, that it's correct. So, wave particle duality. I think this was like in the 20s, 30s. Anyway, these two guys from Bell Labs found out that electrons can act like waves. They did an experiment, right, where they showed that an electron would act like a particle, but then it would act like a wave, and then it'd go back to acting like a particle. It's like if you threw a golf ball or a baseball at a wall that had two windows in it, it would go through the windows at the same time and still would come together as a single baseball on the other side. So, and yeah. So what happened? They had an electron gun. They shoot these beta particles through here, and then it would show up and it have an interference pattern like a wave would have, versus like two little lines here. That means it acted like a wave. All right. I think these are the actual shots, right? So they'd send these things through, and these were the electrons. And then over time, they would see these interference patterns like it was a wave. Weird. Now, in the early 20th century, they were trying to understand how this wave particle duality worked. So Heisenberg, right there is Heisenberg, all right, with his uncertainty principle, and Schrodinger with his wave equation and his cat, but that's totally separate. Now they came up with his wave functions, right, and how to do the math. That's Schrodinger right here. So he had these solutions, all right, for what's going on with electrons, okay, uh, and this is what we're going to really understand or try to understand as we go through the course. So he treated the electron as a wave. So Schrodinger came up with these wave equations that can describe the chance or the probability of where you can find an electron at each location in an atom. So he got his Nobel Prize in Physics, rather, in 1933, less than 100 years ago. So this is all relatively new. So anyway, we'll just scan through these real quick. So let's talk about the quantum model. All right, quantum model. So this is a probable location where an electron is of hydrogen. There's somewhere those little, could be little dots, right? Pixels, where you could find the electron in hydrogen. We can't say exactly where an electron is, all right? Which means that the Bohr picture or the Bohr model with these neat orbits, they're not correct. So we have a probability distribution that gives us a probable location of that electron. Okay? So that would be like the density around this axis. So there are 4 solutions, or 4 numbers that solves the wave equation for these electrons. Okay, and they're called the quantum numbers. The quantum numbers that we might need to worry about are the N number, the principal number, the L, right, the ML, the magnetic number, and the MS, the spin number. So these more or less give you the address of an electron in an atom. So the principal number is the energy level, or the distance from the nucleus. The angular number, L, gives you the shape of the orbital. The ML number is your magnetic number. This gives us the orientation of that orbital in space. The MS number is also the spin number. That gives us the directionality of the electron spin. Is it positive or negative, right, left, what have you? Okay. So let's talk about the principal number. The orbital is where you're going to find that electron. It's an energy level. Energy increases as you increase the distance from the nucleus. All right, so this gives us the energy shell. The values of N are any number equal to or greater than 1. All right, so the larger the value, the further from the nucleus the electron will likely be found. We're going to go run through these real quick. So the other 2 numbers, L and ML, the angular and the magnetic quantum number. All right, so these regions or subshells, they all have a specific shape based on the energy of the electrons that occupy them and their orientation in space. So the quantum number, L, the angular number, designates what's the shape of the orbital. We've got 4 different shapes: the S, the P, the D, and the F. The ML number, the magnetic number, gives you the orientation of that orbital in space. Okay. So here they are. So this is your S, these are your P's. Those are your D's. Notice there's 5 D's, 3 P's, 1 S, and there's 7 F's. 7 F different orbitals. So let's talk about the S subshell. These are spherical in shape, and they're going to increase, the radius will increase as N increases. All right. And really, is there a change in the orientation in space? No, it's just a brown ball. All right. So, yeah, that number is like 0 for the S orbitals. Now, the P orbitals have 2 lobes, rather. It looks like a dumbbell. All right. So, these depend upon the distance and the direction for the center of the atom. Atom. All right. So along this axis, there is a high probability of finding this electron. This way, a low probability, but you got like a greater than 95 between for these. Now, there are three different shapes, or three different orientations for these P shapes. And they're really just along the X, Y, and Z axes in like a three-dimensional thing. All right. The d orbitals, there's no way I can describe those, but notice that there are 5, right? And yeah, there's 5. I can't describe these, but just understand that for every one of those shapes, that's one shape, somewhere along in there, where those shapes are, you have a high probability of finding that electron. And there's 7 orbitals in the F subshell. Okay, and we're just going to move through there real quick. We'll do these in class. Now, the last number is the spin number. This is cool. So, in the 20s, they discovered that the electrons in the same orbital, they won't have exactly the same amount of energy. So, this just depends on what the spin is of that number. You either have a positive spin or a negative spin. All right? A left spin or a right spin in a magnetic field. And, well, we call it -1/2, +1/2. So each of these orbitals, well, not suborbitals, whatever you want to call them, they can only have 2 electrons. So they're able to pair up. Now they don't like each other, all right? They're trying to repel each other, but with opposite spins, they sort of can stand each other, all right? And I'm making this an anthropomorphic to an inanimate object, but yeah, it makes sense. So here's the 4 quantum numbers altogether. Now, no 2 electrons can have the same addresses. So the first one would be 1, 2, 3, 4, so on and so forth. The second one, all right, if it's an S, the number will be 1. If it's a P, it can be -1, 0, or 1. If it's a D, it can be -2, -1, 0, 1, or 2. F, -3, -2, -1, 0, 1, 2, or 3. The magnetic number would be the orientation. And it's going to be -1 ml greater than whatever. Yeah, it's fine. Okay, so the spin number is +1/2 or -1/2. You put all those together, and then you have the address for that electron. Now, some of these combinations are impossible. If you're at N1, there's only one subshell. It's got to be in the s orbital. All right? If you're at N2, you can only have the S and P subshells. Can't have a D. If you're at N3, you can only have the S, P, D subshells. If you're at N4, then you can have all 4 of them. Okay? We don't have a 5th one yet, but we can talk about that. And I'll print this off for you if you want to, or actually you just draw these in your notes or on your periodic table or whatever you want to do. All right? So this is how you can sort of understand it. You can know that in N1 there's only 1 orbital, 2 total electrons. In N2 you can have 2 different subshells for a total of 4 orbitals, total of 8 electrons. Third N level, 3 N level, you can have 9 orbitals up to 18. Fourth, you can have up to 16 for a total of 32 electrons in that level. Let's go through that real quick. And then, we can go ahead and start talking about this. Now, as you get more electrons, they start to not like each other. They're trying to repel each other because they're negative. So, if you got complex atoms, all right, you have some interactions going on at those levels. You got to account for them, all right? So the energy depends on the N, the shell, and the subshell. All right? Now, this is weird. Don't worry about it. We can get it. There are some overlaps in energy. If you notice, the 4S takes less energy than the 3D. 4P, less energy than the 3D. These are the rules. There's a lot of exceptions to these rules, which we may or may not cover some. All right? But understand, these are the rules. Okay, guys. We'll just go with that. This day 2. This is Coach Scott saying we'll get through this. We're going to understand it. We're going to love quantum mechanics and the quantum model. So this is Coach Scott saying, Hullabaloo, connect. Some deuces. See ya.